Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's make a start. So I guess this is our last week before there's a break, right? So then you guys get to go away for a couple of weeks and work hard. I think that's the goal. All right. So what we're going to do today is we're going to finish off chapter 3 and probably start chapter 4, just by way of a bit of a roadmap. The goal being that at the end of this week, you should be able to have a pretty good go at starting the project. That way, if you want to work on that during your 2-week break, you can. So what I'm going to do is I'm going to finish off the chapter 2 bits, and then we'll have a sort of a slight fun interlude, have a look at a couple of different things, and then we'll start in on chapter 4. Okay? All right, so still talking about the rats. We've been fitting models in the last lecture. So we had the data here. We plotted blood loss X versus log of hormone level Y. There's our shape. We fit a model to it. And again, just to remind you, we talked about 3 different ways to fit models. We talked about using L1. We talked about using least squares, and we talked about using this robust method, the Huber method, which is RLM, and RLM lives in the mass library, so we go library mass, and then we should be able to go model equals RLM log Y tilde X. Okay, I'm going to call it fit rather than model, just because a lot of the code in the commands calls it fit. Okay, so there's my fit, AB line, fit $coef, and that'll give me that line that's been fit. All right. So when I finished up last time, we were talking about the 3 assumptions that go with regression, and that apparently some of that later discussion got a bit clipped off in the recording, so I'll repeat that. And then we're going to talk about diagnostics. So diagnostics is the idea of having fit the model, coming back and just checking whether or not the model assumptions were satisfied. So diagnostics is important because once you fit the model, you may not be right. Your model may not be a great model, and you need to be able to have ways to work out, if your model's not great, what to do about it. Okay? So, with that in mind, what are the 3 assumptions? 3 assumptions are linearity, normality of your errors, homoscedasticity of your errors, and then normality of your errors, okay? And I put them in that order because that's the order of importance. Linearity means that your response is linearly related to your independent variable. Now, the reason for that, of course, is that we fit a straight line to it, right? So if there is non-linearity there, your model's clearly wrong at a very fundamental level. So that's a pretty important assumption. You're going to fit a straight line to something, you better be pretty clear that the relationship is a straight line relationship. Now, how do you pick that up? Well, there's a couple of ways to pick it up. I mean, obviously, you can look at this plot here and you can go, does it look like a straight line? So that's your first glimpse of how you might detect non-linearity. But then the second way you might detect non-linearity is to look at the residuals of this model and see if there's any structure to those that suggests your model hasn't picked up everything. Okay? So I'll show you in a second a really simple example of how your residuals can pick that up. But for the moment, we've got that linearity assumption there, and we'll look at this straight line and we'll say, okay, that looks pretty good. Okay, what's your second assumption? Your second assumption is homoscedasticity. Now, the reason that one's important is because if you've got non-constant variance, then that second part of your model where you specify that the errors have constant variance is clearly wrong, and so your model has a deficiency. So that's the obvious reason why it's wrong. The sort of less obvious reason, the sort of non-techno reason, is because constant variance gives you some surety of quality of prediction as you move across your data. If the variance is not constant, then as your X changes, the quality of your predictions will change. And that's something that's a bit alarming, right? Because if I say to you, predict for me what the value of Y is when X is a certain amount, okay, the quality of that prediction will depend whereabouts X is. So if X is out here, for example, on the high end, and you've got heteroscedasticity, your predictions will probably be worse, whereas at the low end, they'll probably be fine. And on the original data scale, before we took logs, that was what would happen. For low X's, predictions would be pretty tight. For high X's, predictions would be pretty bad. And that's something that, gives people a bit of pause. So that constant variance assumption is your second most important assumption. Now, the third assumption, which we talked briefly about last time, this is where the recording would have got cut off. It's kind of important, but kind of not. Okay? And I'll tell you what I mean by that. Normal distributions have some properties that are very nice. They're symmetric, for example. So the symmetry of the distribution of errors is something you probably do want, because that symmetry tells you that when you miss the line, you miss about as much below as you do above, right? And that's kind of sensible. The fact, though, that the tails of the distribution of errors look like normal tails is somehow less important, because the reason that you require normality is so all your t-tests work the way you say they do, okay? Now, if your t-tests give you a 5% error and your actual error is 6% because your original errors weren't really normal, then there's an extent to which you don't necessarily care so much about that. 0.05, 0.06, what's the practical difference, right? So when your errors are not normal, the main impact of that is that the tests you do that follow the regression tend not to be exactly at the right level. But, unless they go hideously out of track, you're not so concerned. So we worry about normality as an assumption, but we don't worry about it as much as we worry about homoscedasticity, and certainly not as much as we worry about linearity. Okay? So that's where we're headed. Now, how do you detect any of these things? Well, we've talked about different kinds of plots that you might produce. So the first one was the residual plot. That's pretty simple. So I'm going to do these one by one. Plot X against $fit resid. And this is our residual plot for this particular data, okay? Now, typically, you would add to this plot a horizontal line at 0 because your errors should be equally above and below 0. And then what you do is you look at this plot and you take two fingers, one that sits above and one that sits below, and you track across. And basically, you want that thing to be flat and you want it to have constant width between your fingers. So if I say to you, look at that plot, tell me what it looks like using your fingers. If you're doing a flat, constant width shape, then everything's good. Now, when things are not good, they can be not good in a couple of ways. The first thing that can happen that can make them not good is that your hand has to move. It doesn't stay flat. If your hand has to sort of go up and then down, that's a sure sign that your residuals haven't captured some structure. So that would tell you that there's nonlinearity in your data, okay? Really easy to see in a residual plot. Let me show you an example. Let's let X equal a sequence that goes from 0 to 1 in steps of 0.01. Okay, so I'm just going to break up the 0, 1 into 100ths. And Y is going to be just X squared plus a little error, right? So R norm, I bet length of X should be 101 maybe? Yeah, 101. So Y is going to be X squared plus R norm. I'm going to generate 101 of them, mean 0, and I'm just going to have a little variance here, 0.0, 0.005. That'll do. Okay, I'm going to plot xy. Now, you can see it looks like not a straight line, looks like a curve. And you can see there's a little bit of noise in there, right? Now, if I jack up that noise, right, instead of 0.005, I make it 0.01. You can see it starts to look a little bit less serious of a curve. Let's jack it up a little bit more. And so the curve's still there, but it's hard to see. Okay? You might fit a straight line to that and think you're okay. So it's easy to do, right? Let's fit a straight line to that. So let's go AB line, RLM, Y tilde X. There's my straight line model. Look, it's not a dreadful model. It goes kind of through the middle of the data, but you can see it sort of misses here, sort of starts to miss here a bit, but it gets better, and then it misses up the top. But, you know, if you just looked at this, you might go, well, it's good enough, okay? Let's have a look at the residual plot for this, and you'll see something really interesting. Now I'm going to plot X versus RLM Y tilde X dollars resid. So this is the residual plot. And when you look at the residual plot, you'll see there's a very distinct curve to that, right? If I got you to do the finger thing, your fingers would start high, then they'd come down. They're staying the same width apart, that's cool. They'd come down and then they'd go back up, right? So when you look at a residual plot, this is raw residuals, not absolute residuals just yet. If you look at a raw residual plot and you see a shape in there, then that's generally a sign that you've missed something in your model. The linearity assumption is not valid, okay? So shape in the residual plot that looks like the plot's going somewhere is an indication of non-linearity. So that's thing one. Heteroscedasticity is governed by the idea that your fingers don't stay, your fingers don't stay the same distance apart. So this is homoscedastic because as I move along this, my fingers don't move further apart, they stay the same distance apart. They just don't move in a flat shape, okay? So this is non-linearity but homoscedasticity, all right? So curvature in a residual plot tells you about non-linearity. That's why you do the raw residual plot. Okay? Now let's go back to my original RAT data, because I want to keep playing with that. So X is going to be this now, and Y is going to be this again. I've already fit the model to it. I called that thing fit. So we had a look at X versus fit dollars resid. So that was my regular residual plot. Okay, looks okay, flat, and fingers stay roughly same distance apart. I put in this AB line, H equals 0, okay, but I have to look above and below that line in order to see homoscedasticity. So the next plot I typically produce is an absolute residual plot. So first plot's just a regular residual plot, second plot, an absolute residual plot, so I go plot X, absolute value of fit dollars resid. So this is my absolute residual plot, and then I'll typically go lines low S of X absolute value of fit dollars resid. So I just throw a low S curve through this plot. Now here what I've done is I've folded those errors so that the below zeros become positive, and this is so I don't have to use two fingers anymore. I can just use my index finger and it floats above the 0 line, and this one here, I've got a low S curve, I don't need my finger anymore. I can just do what the low S curve does. It kind of goes down a little bit and then flattens out. And you might say to me, I'm a bit worried by this, it's going down a little bit. The reason it starts high is because of that large number of things at 0, okay? Not so worried about that, I think it's an edge effect. I think this is pretty flat. And remember, we're dealing with real data here, right? So perfectly flat ain't going to happen. You can get it looking mostly flat, you're pretty happy. So the first plot you produce is a raw residual plot. You use that to see whether the thing exhibits non-linearity, okay? That's first task. Second task, absolute residual plot with a low S curve through it. If that low S curve is relatively flat, you've got homoscedasticity. Second assumption, good to go. Third plot you produce is a QQ plot of the residuals, the raw residuals, not the absolute residuals. Yeah. Well, for simple linear regression, it amounts to the same thing because the fits are just a linear function of x. Once we hit multiple regression, we don't have a single x to plot against, and then we plot against fitted values. So, yeah. Okay, so the next plot, QQ plot of the residuals. So remember, for QQ plots, they like being square. So par PTY equals S, QQ norm, fit dollars resid. There's my QQ plot of the residuals. And then typically what I like to do is put a horizontal line at 0, a vertical line at 0. By the way, the reason they're both at 0 is because these are errors, and so errors should have middle 0, okay? And then a QQ line. And if you want to de-emphasise these lines, you can make them grey. So, okay? And you can see here, there's my QQ line. You can see it sort of misses at the bottom. It sort of misses at the top. This looks S-shaped, so it looks like my residuals are mildly non-normal. They're a little bit light-tailed, okay? And remember the golden rule in life, right? If you want 3 things out of something, choose 2. It's probably what you're going to get. So we got linearities okay. We got homoscedasticities okay. We got normalities not quite okay, okay? And what that means is if you do t-tests on this, when it reports a p-value of, you know, whatever it does, and I'll show you the p-value in a second, take that with a grain of salt, okay? So let's have a look at that. Let's have a look at the summary of my fit. And you can see the summary of my fit says, there's my intercept, 0.44, there's my slope, 0.14. Here are the t-values, okay? So my slope is 17 standard errors away from 0. So the p-value associated with that will be 0.000001, be small, right? I know that's not going to be exactly right because my errors aren't exactly normal, but it ain't going to get up to 0.05, is it? So this regression is significant. And again, your eyes tell you that, right? So these t-values tell me that I don't really care if my p-values are out a little bit. They're not going to be so far out that I'm going to be hideously wrong about the test. So that's cool. So there's really no problem there. And I don't worry about it as a result. Okay? Now there's one more plot that's worthwhile doing, and it's called a leverage plot. Last week we talked about points with high leverage. And points with high leverage cause problems for the model. There is a calculation you can do in R which calculates the leverages of the data, and the function for that is called HAT, H-A-T, HAT X. Now, there's a reason it's called HAT X. It's because the leverages are related to the transformation or the projection that takes your data and produces the fitted values. So, if you've done a regression course, and again, if you haven't done a regression course, doesn't matter. What I'm about to say won't make much sense. I just want to explain to people why it's called HAT. In regression, y hat, the fitted values, is equal to the projection matrix H times y. That projection matrix is called the hat matrix because it takes y and puts a hat on it. That's it, right? So a silly reason, but that's what it is. So hat of x calculates the leverages. And what we typically do in regression problems for simple linear regression is you do a bar plot of the leverages, bar plot of hat x. So this is a bar plot of the leverages for my data here, okay? Now, for simple linear regression, the average leverage is 2 divided by sample size, okay? So, now, that can be proven, but it's not our goal here to prove it. So I'll just tell you that. It's 2 times this, 2 divided by sample size. So quite often, when we look at a leverage plot, we put a horizontal line at 4 divided by the sample size here is 92, and anything above that has twice the average leverage. Okay? So these are the points that are above that line that have more than 2 times the average leverage. These are your possibly influential points. Okay? Now, generally speaking, remember what I said last time. Leverage points are trying to pull the line through themselves. Okay? If they've got very high leverage, they might succeed. If you've got a lot of points with high leverage, you've got to imagine a data set where there's lots of different points pulling the line towards them. They're not all going to be necessarily in the same place, and so the effect might be null. Okay? The thing you generally worry about is when you've got one big influential point. Now, to talk about that, I'm going to go back to Anscombe's data. Remember Anscombe's data? We talked about this quite early on in the course. This is this data set where you've got 4 x's and 4 y's. Okay? You remember we plotted each of them out, and the last one of these has an influential point in it. So let me show you that. So I'm going to attach Anscombe, and I'm going to plot x4 versus y4. Okay, so there's Anscombe's data there, x4, y4. I'm going to go AB line, LM, y4, tilde, x4, dollars coef. There's the fitted line. Okay, so this is a sure sign that I've got high leverage, right? Because what happens is you want to fit the line that goes like that, but instead that point over there pulls the line through itself. It levers that line over. Okay, so this is a point that has high influence. It has high leverage. I want to show you the leverage plot for this data. So I'm going to do bar plot of x4. A hat of x4. Okay. Each of these data sets has 11 points in it. So AB line, H equals 4 on 11. There's one point that has high leverage. Okay. When you've got a picture that looks like this, you've generally got a problem. Not always, generally. Okay. So you can use the leverage plot to detect points that have high influence, potentially high influence. Okay, now, how do you put all this together? So once you've finished fitting a model, these are the 4 plots you'll want to produce, okay? You'll want to produce a regular residual plot. You'll want to produce an absolute residual plot with a low S smoother through it. You want to produce a QQ plot of the residuals, and you'll want to produce a leverage plot. These 4 plots will test linearity, homoscedasticity, normality, and they'll tell you whether you've got potentially influential points. So this kind of wraps it up in a nice neat bow. Because I've got 4 plots to produce, I'll typically do it like this. Par MF rho equals C 2, 2. Then I'll do residual plot. Okay, usually I'll do that one first. There it is. Then I'll put the line in at horizontal line at 0. Okay, plot number 1. Now I've noticed the plots are still square. I didn't want the plots to be square. So once you make a mistake, scrub it, do over. Okay, first plot, there's my residual plot. Okay, so you do that plot first. Then you do the absolute residual plot. Okay, so where is it? There it is, absolute residual plot, pop on the lowest smoother. Okay, there's my absolute residual plot. Next you'll do the QQ plot, QQ norm. Where are we? QQ norm. First, par PTY equals S, then QQ norm. Okay, do that one, put on the QQ line, put on the crosshairs. Where is it? There. Okay, and then finally, you want to go back to par PTY equals M, because you want this plot to take up the whole thing. You put on your bar plot of leverages. Where is it? There. And then the reference line at 4 divided by sample size. okay? So this set of 4 plots is kind of like your set of diagnostics. Did my model fit okay? And then you basically run through them. You go, first one there, looks pretty flat, fingers stay roughly same distance apart. Because it looks flat, I think my linearity assumption was okay. Thumbs up. Second plot, absolute residual plot. That low S curve looks pretty flat. Data's homoscedastic. Second assumption, seems to check out. Good to go. TQ plot of residuals, a little bit S-shaped. So, life's not perfect. My p-values are probably not going to be perfect. Whatever. Okay? And then finally, do I need to worry about any points of high leverage plot? Okay? These 4 plots tell you how your model fit. And if it fits okay, you're good to go. You then report the model and you're done. All right? Reporting the model means writing down what the model is. So, when you do your assignments on your project, for example, after you do these diagnostics and you decide your model's okay, you then write down what the model is. If you don't write down what the model is, it's like not reading the last page of a bloody good book, right? People will be going, is there more? It'll be like a Marvel movie. You walk out going, what just happened? Is that it? Is it finished? No? I watched, what was it one? The last Marvel thing where everyone, who hasn't seen it? Who wants to see it and hasn't seen it? Anybody? Do you want to see it? Can I spoil? Everyone dies. Like Spider-Man dies, what the hell? And now they're making a new Spider-Man movie. How's that going to happen? Anyway, maybe spiders have 9 lives, I don't know. I thought that was cats. Anyway, I don't get it. Anyway, Superman's died about 7 times, right? So, whatever. I don't get it. Anyway, yeah, if you don't tell me what the model is at the end, it's like not finishing the movie or the book. You know how bad that feels? Yeah? So whoever's reading your report, if they don't get the model, you know how bad they feel? If they're paying you, you don't want them feeling bad, right? Simple. So make sure you write down the model, okay? So in this case, what's my model? So my fit was this, okay? So I write down my model. My model is log y equals 0.44 plus 0.14 times x, okay? So that's my model. Not quite right. You'll notice I never write plus error at the end. And the reason I don't write plus error is I fit the thing. Once you fit it, the error is assumed gone, okay? But that's not quite right yet because it's in terms of log y, right? So I need to write this as y equals exp 0.44 plus 0.14 times x. So that's how I would write it. So there's my formula. Now, almost done, almost done. Nobody likes talking about y's and x's. What you should write is AVP, that's your hormone, is equal to exp 0.44 plus 0.14 times blood loss. Right, write it in English if you can, or as much as English as you can, right? Remember, this is to give somebody, telling them what's going on. If you just say X and Y and they don't know what X and Y is, you might as well have just said blah, 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 right? And they won't respect you anymore, okay? So always write down your model. Okay, so this is part of what I would call good modelling hygiene, right? So it's like cleaning your teeth. Fitting models is terrific, and yes, statisticians are some kind of gods for being able to fit models to messy data. But wrapping it up and making sure that the model assumptions are satisfied and writing down your model at the end, that's like cleaning your teeth at night, okay? Very important to do, otherwise people won't like you, people won't talk to you, okay? So, in this course at least, when you finish off your modelling, don't just go, that's it, and don't tell me these diagnostics and don't show me the final model, okay? If you do that, I won't like you, right? At least I won't like the assignment version of you, right? You might be a fine person and all that, and I might think you're terrific, but I won't like your assignment, okay? So make sure you wrap those things up, they're very important. Okay, now, let's have a look at this for a different data set. You'll remember that Raptor data. So let me just go back to Waddle here. We talked about this a little bit earlier. This is the data on egg volume and female weight for a bunch of different birds of prey. So let me just grab all of this, copy, and dive over to R. And I'm done with the rats. You can all say, thank God he's done with the rats. I was tired of the rats. Okay, so let's just work through this. So you remember the raptor data. So there's X and there's Y. There's my first couple of plots. Okay, so this is the first plot's X versus Y. You can see it's not linear, very evidently it's curving, and it's heteroscedastic. And we discovered, we did this the other day, that if you take logs of both of those variables, you straighten it up. Okay? So that's where we're at the moment. All right. So let's go through, and I'm just going to clean out, remember there were missing values in this, I'm just going to clean them out. RLM is not tolerant of missing values, so you need to clear them out before you go. So I'm just going to fit a model relating log y to log x over here. Okay, and now I'll have a look at a summary of the fit. There's my summary of my fit right there. You can see my t-values are ginormous, right? The intercept is 102 standard errors away from 0. The slope is 72.5 standard errors away from 0. So the regression's highly significant. Again, your eyes tell you that. Your eyes tell you that. So no surprises there. All right, now what I want to do is I want to go through and do my residual plots. Okay? So let's go ahead and do that. So I'll clear off this workspace here. I'm going to do them one at a time. Normally I'd lay them out in that 4x4 grid. That's what you should do. The reason I'm going to do them one by one is because of size. I want you to be able to see them. All right. So let's go through and do the residual plot. So I'm going to start with the QQ plot. Okay, there's a QQ plot of the residuals for my log-log model. Look at that. You probably can't do better than that. Right? You probably can't do better than that. So it's about as straight as you'll get. All right, let's have a look at the raw residual plot. We need to set par PTY equals M. We've done that. Raw residual plot looks like that. Okay, what's going on here? Get your two fingers out. Looks pretty flat. Fingers don't really move too much further apart from each other. So it looks all right. Pretty noisy, but not too bad. Some people see a little bit of a curve in this, mainly because of this point down here. But this is one point out of lots, so probably I would say that's good to go. Okay, so I don't see any problems with linearity. Again, I would probably add the horizontal line at 0, AB line H equals 0, just for reference. I think that helps. Okay, here's my absolute residual plot. Let's do that one. And there's a low S curve running through it. Again, just that suggestion that it's a bit high here, but then it flattens out. Okay, I think, again, this is an edge effect, nothing too much to worry about. So we'd probably say your assumptions there are okay. And then I should be able to do a bar plot of hat. Remember, my response here is log x, so bar plot of hat log x. Okay, looks like that. AB line H equals 4 on length of x. My sample size is length of x. You can see there are quite a few points that might have reasonably high leverage, but again, because there's so many of them, I don't really worry about it. They're all pulling in probably different directions. If I don't see any evidence that the model's wrong, then this is what happens. Now, I just want to return to one more, so that's it. Now, again, what did I not do? I didn't write down the model. Should write down the model. So, hashtag log y equals, and what do we have? It's drifted off the top of the screen. It's about 6.2 and 0.68, so 6.2 plus 0.68 times log x, okay? Then make sure you come through and write it as y equals x, whatever. And then make sure you come through and write it as what it should be, which is female weight equals ... as a function of egg volume, right? So write it in the original variables. So always write down your model, okay? I'm typing ... so you don't have to watch me fluff around trying to type weird numbers, okay? So that's the Raptor data. And so again, it's that same kind of thing, right? You go through this exploration process of taking an original data set. If it's not linear or it's not homoscedastic, you've got to work out what the shape is. LOS will help you do that quite often. But as soon as you can, you typically then try to proceed to regular modelling, linear modelling if you can do it. And then it's really just a process of working out, do you need to transform your data in a particular way to make it linear, fit the model, then go through this diagnostic phase. Okay? So that's kind of the bottom line. Now I want to make one more point about leverage. So again, I'm going to go back to the Anscombe data, and except now everything's in caps. I don't really know why. Probably because I hit caps lock. Okay, so there's my Anscombe data again. Remember, I'll call it fit1 equals lm y4 tilde x4. Okay, AB line, fit$1 coef. Okay, so there's my line. I just want to show what the residual plot looks like when you have a point of high influence. So let's have a look at a plot of x4 versus the residuals for fit1. That's what my residual plot looks like. And I'm going to put a line, AB line, at h equals 0, like I would normally do in a residual plot. See how weird that looks? Now, I wanted to point something out to you. The point that has high influence is that one over there, right? Right on the edge, okay? What's the residual for that point? 0, okay? So, think about the difference between outliers and influential points. Outliers have high residuals, right? They're away from the model. Influential points hide themselves in residual plots. They almost always have low residuals because what they do is they pull the model through them and then they're sitting there hiding, right? So anytime you see something like this where your suspicious point is hiding there with a very small residual, that screams that you've got an influence problem, okay? So when you look at residual plots, outliers hang around at the edges. They really are the outsiders of data analysis, right? But influential points, even though they're bad, they're like the insiders, right? They suck the model close to themselves and then they hide, right? And that's why you need to look for them as well as looking for outliers. Okay, on we go. So we're going to start talking about the next chapter, but before I do that, I'm going to have a tiny break for a bit of fun. When I say break, you guys still have to sit there and listen to me, isn't that sad? But anyway, so I've added some new stuff to the fun links here. So those things I showed you last week, I put a link to that up. But I wanted to talk about a couple of things. Oops, I've already got that up. So the first one is about this 0.05 thing. We talked about this idea that when your residuals aren't normal, your tests don't have the right level, right? And so if you're worried about what 0.05 does for you, then you worry about normality more. So this is a copy of an article that was in a magazine. So statisticians, so you know how you go to the supermarket and there are magazines there, right? You know, Men's Health, which typically has some guy on the cover who looks really healthy. What else they got? Better Homes and Gardens, which always looks like my home doesn't, and all that stuff, right? So, you know, statisticians have a magazine. We do. It's called Significance. Seriously, we have a magazine. It's a pretty good magazine, actually. You might think, no, it's probably not. But it actually is very interesting. Anyway, their first issue, they had this article, Does Significance Matter? And it's a big discussion around statistical significance, right? And I just want to draw your attention to one little bit of this. and that's on the right-hand side of this page. So let's drift over there. I'll make it uncomfortably large. Okay, so that's a picture of Sir Ronald Fisher, right? Doesn't he look adorable? And this is where 0.05 came from. The great R.A. Fisher wrote in 1926, "Personally, the writer prefers to set a low standard of significance at the 5% point and ignore entirely all results which fail to reach that level. A scientific fact should be regarded as experimentally established only if a properly designed experiment rarely fails to give this level of significance." Okay? That quote started everything. So since then, science has had, you can only describe it as a fetish for 0.05. You go to any journal, medical journal, psych journal, social science journal, any journal in which data is used, if they fit models, you'll see little stars next to all of the tables of the coefficients, and you get 1 star if you're significant at 5%, right? You get more stars if you're significant at lower levels of 0.01 or whatever. But 0.05 is kind of like the gold standard, right? And it's the gold standard because he said that. Now, if you look what he actually said, it doesn't marry up with what people do, right? He said, a properly designed experiment. Now, most of the data you get these days is not from a properly designed experiment. It's from an observational study. You measure X and you measure Y. That's not properly designed. That's just getting data. And that's different, right? So he says, use 0.05 in a properly designed experiment. And he had in mind agricultural field trials in the UK, where you had sample sizes that were kind of small, okay, and 0.05 kind of made sense in that context. And remember, 0.05 is your type 1 error. It's the error you will tolerate. I'm happy to have a 5% error in what I say. Now, in an agricultural field trial, that might be fine. But if you're talking about diagnosing cancer, it's probably not fine to have a 5% error, okay? And if you're talking about something that really doesn't matter, like who's going to be the next Prime Minister of this great country, because God knows we'll have another one by noon, then maybe a 20% error is fine, okay? So what Fisher said and what people do are two different things, and yet everybody does it. And it is maddening, right? And so I just want you to be aware that this 0.05 is, and I can't say it any other way, it's bullshit, right? It just is. What he said isn't wrong, but what he said is very specific. What people do is far too general, okay? And that's a problem, and it's a big problem in science today, okay? And you might go, why do scientists do this? Well, I'll tell you why scientists do this. Scientists do this because scientists use statistics like a carpenter uses a hammer, right? It's not his go-to tool, but it'll sure as hell bang in a nail. Well, that's how scientists use statistics. They've got a problem. They're not statisticians, they're scientists, right? Quote unquote. So they've got data, they want to prove what they want to prove, so they think that's a nail, so out they get the hammer, bang, 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 oh, 5%, problem solved, I'm now famous, pay me money, da-da-da, right? Well, great, but that's not thinking. That's just using something to bang in a nail. And you know what? Most scientific problems aren't nails, they're screws. And if you bang in a screw with a hammer, you get the thing in there, but it's a mess, okay? So statisticians really should be quite bullshit about this and be telling people, no, 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 think about what you're doing. Don't just apply the 0.05 rule blindly. And in fact, Fisher never said to apply it blindly. He said, do it in these cases. He didn't say what to do in other cases. The problem is, everything now is other cases, and yet we still follow Fisher's rule. So, be careful. Be careful. Okay, look, this has become a thing. And this has become a thing in science now. So a couple of years ago in Nature, so Nature is one of the big science journals, okay, they published an article about p-values. This is a good read. So I've put the link here to this, and it talks about all the problems with p-values, okay? Really worth reading, really worth reading. Again, it's not really part of this course. It's got nothing to do with graphical data analysis. But remember, the journey we're on isn't a journey just to learn a really narrow topic and come out at the end with a good grade. The goal is to become educated in the ways of data, all right? If I do that for you, I've done way more than I can do by giving you an HD because you know a tiny amount about a lot, right? So I'd love you to read this. I can't force you and I won't, but I think these things are really important to think about. So this is about what currently seems to be a crisis in science around the use of p-values, and it's well worth thinking about. There is one journal that has banned p-values, okay? It's a journal in psychology. I don't know how that's going for them, because that's like standing at the edge of the water and saying to the waves, don't come in. They're coming in, folks, right? A lot of people still use them, but it's the start. And look, I predict that in maybe a decade's time, statistics will have utterly changed. P-values won't be the currency they currently are. So you have to start thinking about evidence more holistically now and not just reduce everything to a stupid p-value judgment, okay? So this is why, of course, graphical evidence is so important, right? Because graphical evidence supplements these kind of colour by numbers 0.05 judgments with visual evidence that help you really close the loop on what's happening and what's not, okay? And so that's why I think a course like this makes sense. All right, that was today's fun. Very serious fun, wasn't it? You know, don't do this or you'll be in a lot of trouble. But anyway, it is what it is. Okay, we have 4 minutes left. So in 4 minutes, I could let you go early, but what would be the fun in that? Okay, everyone's happy to stay, good. So I didn't give you a chance to say no, let us go. I'm going to tell you about babies. Everyone loves babies, right? This is not a great baby story, but anyway. This is our next data set that we're going to lead into. So I'm going to tell you about the data now, and then tomorrow, hopefully, everything will work in that other room, you know. We'll go there and we'll just hope for the best. We'll start talking about the babies. All right. The thing about the stuff we've been doing so far is it's got one X and one Y. And if only life were that simple, we could wrap up the course now and you could go home for the rest of the semester. But life ain't that simple. Life these days is intensely multivariate, right? Lots of variables, and we need to work out how they relate to each other, okay? So this is an example of that. We've got data on the birth weight of babies. So you've got, how many babies were there? 247 babies. The data consists of their birth weight in grams, their gestational age, which is the doctor's best guess of how long the baby's been inside mum, okay, until it comes out. Things called 1 and 5 minute APGARs. So these are numbers on a 0 to 9 scale. At 1 minute, they look at the baby and they basically say, is it breathing, is it blue, is it this, is it that? If you get a 0, basically not good, nothing's going on. If you get a 9, you're doing differential calculus, right? So 0 to 9, 9 means you're good to go, 0 means you're probably not good to go, okay? And they do that at 1 minute, and then, you know, we think 5 minutes is nothing, but in the first minutes of life, it's everything. So between 1 minute and 5 minutes, a lot can change. So they take these APGAR scores at 1 minute and then at 5 minutes, okay? And then, I didn't know this, but when my son was born, the first thing they did after they checked the APGARs was they got a little needle and they took a little bit of blood out of his heel. And I'm like, why are you doing that? It turns out what they do is they calculate the venous pH of the baby's blood, the acidity of the blood. And this is supposed to help them work out something, I don't know what, about the viability of the baby, okay? So those are all our variables, right? We've got weight, gestational age, 1 and 5 minute APGARs, and venous pH. Then our response variable is a bit sad. These are premature babies. It's a survival variable. If the baby does not survive, they get a 0, and if they do survive, they get a 1. And people say to me, why are you telling us such sad stories? We don't like to hear about babies not surviving. But remember, most of statistics is all about how do you fix things, right? So babies not surviving is bad. Let's try and fix it by understanding data around this. So that's why. Look, in some countries, child mortality is a terrible problem. Right? We saw, remember Hans Rosling? He spoke about child mortality. In some countries, it's very, very high, like 47% of babies don't survive. Here in Australia, it's, thank God, very low. Okay? So, we're interested in knowing how these variables relate. you've got 5 x's and 5 x's, I think 5, and 1 y. So how do we start to pull all that together? So let's get the baby data. I don't have it up there yet. I'll just show you very quickly. And of course, I'm going to have to do this again tomorrow because presumably the recording's about to cut out. But let me show you very quickly a couple of plots.